Okay, let's go ahead and kick everything off. Hi, everyone. My name is Mandy Aulick. I'm on the marketing team here at VAST. I just wanted to kick off this webinar before I pass it over to Suyash, who will be presenting today. So welcome to the live session for From Stream to Action, Simplifying Real-Time Data Analysis and Operational AI for the enterprise. I just want to take a quick second here just to go over some housekeeping. We will have some Q&A at the very end, but feel free throughout the presentation to submit your Q&A on the right-hand side. And if you want it to be anonymous, just click on the box below where it says hide name. And we'll make sure we kind of get through the questions at the end of the presentation. And if we run out of time with any of those questions, we'll definitely make sure we reach out to you, but hopefully, we'll keep everything on track to go through those questions. And as well, we have some additional resources for you in the docs section. There's, links to our demos page. There's also a link to additional resources regarding this session. There's a blog post that's really great, that's relevant to the session that you may want to read as well on the side or, later. And then also if, we have some regional events. So if you're in those areas, take a look and please sign up for those. I am going to now pass it over to Suyash so he can do his introductions and go through the session with you guys. Thank you.
Sounds good. Thank you, Mandy. Let me share my screen so everyone can look at the slides. All right, I hope you see my screen. Hi, this is Suyash Ramneni. I'm a senior systems engineer at VAST Data. I primarily focus on data analytics and enterprise AI here at VAST Data. Today, we're going to talk about a new product that we built at VAST, and this is all about real-time data streaming and running, queries on it or getting an event and taking an action on that, right? So that's why the talk today is titled From Stream to Action. At VAST, we are building the data platform for the future, for the AI era. And we have talked with many customers who have problems with data management, right? And we're working with our potential customers and existing customers to re-architect the data platform by making sure that they can get insights out of both real-time data and also batch data as well. So let's take a look at some of the problems of the last 2 decades. Data management has been quite complex for the last 2 decades. Data management itself requires storing data, obviously, and processing it. But for different use cases, you need different architectures. Obviously, we have OLTP databases to manage transactional information. And then we have event streams to get the data in real time and again, store it and take action on it. So these are, again, siloed deployments of infrastructure and software to manage different kinds of data. Then to run analytics on this data, you would have to create a data warehouse by transforming the data from both OLTP systems and event streams, right? Now, it's all structured and well and good, but when there is unstructured data, you have to build a data lakehouse environment to make sense of both the structured data and unstructured data. Many customers struggle with, building a single instance that can, cover all these use cases because that's nearly impossible. And there are no solutions out there that actually scale effectively to manage different workloads on the same system. So this has been a huge problem for a lot of customers, and that creates data silos within an enterprise. These silos also lead to other problems where consolidation or making sense out of data coming from 2 different systems becomes complicated. So we are trying to consolidate and help our customers by trying to get rid of different systems as much as possible and consolidating data lake, data warehouse, and event streams into a single architecture wherever possible. So today we are going to talk about event streams, event brokers, and events in general. So let's get into events. There are events everywhere. There are going to be multiple examples of events, but at a high level, you can classify them as notifications or any kind of state changes. So essentially, it's a small message with some information. There are two types of events: human-generated events and machine-generated events. A few examples of human-generated events are going to be, a small credit card transaction could be an event. A movement in stocks itself is an event if you want to take an action on that. And a simple, user click on a web page, or even just browsing through, moving your mouse across the web page could be an event, depending on what someone needs to do with that information, right? So there are several events that get generated in a single second across the board, and it's up to the business to determine which events are valuable to capture and make and store and make sense out of, and which events can be discarded, right? But that's just human-generated events. The scale of managing events dramatically increases when you have machine-generated events. So in a manufacturing deployment, you have so many IoT sensors, and you have log information, you have sensors that send out events. All of this is machine-generated event that needs to be tracked for different reasons. If you want to track the machine manufacturing lifecycle and you want to prepare for downtimes, you need to capture those messages and try to predict if a machine is going to be down in the next hour or in the next day due to wear and tear or some error that may or some warning that has come up, and it may cause an error later in the day. Similarly, traditionally in software development, we have a lot of applications and microservices talking to each other. And usually, the way they communicate with each other is through events and messages. So that's also machine-generated events. And similarly, as we have a lot of telecom networks, they have multiple events. Every call you make is an event. Every text you send is an event. Any downtime of the tower is an event that needs to be captured and rectified. Your call needs to be redirected to a different tower, etc. Right? So the volume of machine-generated events is much, much higher than human-generated events. However, for a business, it's important to classify these events effectively and make sense out of them, right? Depending on business needs. So we have already understood events are everywhere. We know that. But based on business requirements, events are quite powerful. So we need to make sure that these events are captured effectively, efficiently, and then processed. Typically, an event is just a key value message, right? So you have an ID and a message, or a specific set of values monitored by a key identifier. Now, as we discussed, events can just pile up very, very quickly. And it's very hard to kind of capture them and make sense out of them because they can just balloon up very quickly. This is the key problem that several organizations faced. And eventually, there were systems designed to capture large volumes of events. However, the technology to store these events and process these events was based on really old research papers developed at Google. So about 20 years ago, 2 decades ago, right, Google launched two key research papers. One was GFS, the Google file system, and the other was MapReduce. So GFS was a mechanism to store large amounts of data into a distributed file system called GFS. And there were open source projects that propped up to imitate that file system or the architecture of the file system. And that gave birth to several technologies, such as Hadoop, HDFS as a file system, and Kafka as well to some extent, right? The Kafka architecture is very similar to the Hadoop architecture, where you have multiple nodes and there are events coming into Kafka and they're consumed as well. Right. So we are going to draw parallels with Apache Kafka in this presentation because we have determined that that is, the most easier way to understand how Vast Event Broker works. That's one. And the second is we're going to learn a little later in terms of how we compare with Kafka. So the other research paper I talked about was on MapReduce, which is the compute framework on GFS. And even though Kafka doesn't incorporate it, there are other frameworks like Hadoop that incorporate it. So we are going to skip on that. But this is an architecture that is 20 years old, and this was not built for the future. It worked for a while, and then it became quite complicated to manage. If you have to deploy a architecture that is based on direct attached storage and compute in a single node, that's basically a shared nothing architecture. And it has a lot of problems with it. So let's take a look at some of those issues. So the challenges of this architecture are you have rigid nodes that can't necessarily scale. To scale the architecture, you have to add additional nodes. And what happens there is you have to have both storage and compute to manage the distributed computing framework from scaling both the storage and compute effectively, even though in applications where you don't have storage requirements, growing, you would still have to continue to add storage nodes with compute attached, right? The performance challenges come up with I/O, where multiple nodes have to talk to each other. So there's a lot of east-west traffic, and that slows down the data retrieval process, right? Also, this architecture is not designed for high performing SSDs. It's mostly designed for low performing hard disks. So from a cheap commodity hardware perspective, it makes sense to some extent, but at scale, this architecture becomes too complicated to manage, and many customers are trying to move away from such a deployment. Now, what we decided to do and build a platform around is called DAYS architecture. So this is a new parallel architecture where everything is disaggregated and shared everything, meaning we have a concept of C nodes and D nodes. So data is stored in D nodes, and all of the compute requests are managed by C nodes. Every C node here runs multiple containers, and let's assume this being a C node container, it can have access to all of the D nodes data, meaning every container can see everything. So this is a shared everything architecture rather than shared nothing architecture. The other aspect is we have completely disaggregated architecture, meaning you can add multiple D nodes if you need to scale storage, or you can continue adding C nodes if you only want to scale your compute needs. So that's the beauty of this architecture, which takes away all the problems of shared nothing architecture. And as I pointed out, it's very easy to add additional hardware and grow the cluster asymmetrically without any problems. Now, what we added to the architecture are multiple protocols and applications that customers can leverage, users can leverage. At a high level, we have protocols for storage, as pointed out here. We have protocols and plugins for SQL layers, as mentioned here. And additionally, what we are calling out today in this presentation is the Vast Event Broker. Vast Event Broker runs on RC nodes and is able to capture multiple messages that are written to it and provide access to consumers that can consume those events. Now, let's take a deeper dive into how Vast Event Broker works and manages the events in key value form. So ultimately, all these events can be logged, and the log is append only. So let's take a deep dive into that. So you can think of it as a single log, starts with a single message, and the log keeps adding messages, right? So every new message gets written at the end, and that allows you to have an append only log. Now, that can just keep on going. That allows us to continuously store messages, events as the data is being generated, right? Now, every new message, as mentioned, is added at the end of the log, and the entire log is immutable, meaning you're not changing data, it's append only. That way, you can consume, you can also log the changes of a message at the end, and you can start consuming the data as well. Now, what is this log? Essentially, it's a topic. So these topics are similar to tables in a database, and simple examples are, multiple user clicks that can be captured on a website, sales orders that are received for an e-commerce or retail website. All right, so you have these events coming in, these orders coming in, and they are logged as they come in. And maybe in real time, you want to consume information about okay, what were the amount of sales that happened in the last 1 hour or 15 minutes or 5 seconds, right? And that can happen in real time. So similarly, you can store information about customers and whatnot as you keep adding new customers in your users table or customers table. So at the from a functionality level, each topic in Vast Event Broker is very similar to a table in a database, right? Now, the other aspect is if you have multiple sources to write from, let's say you have multiple stores and orders are being generated from multiple stores, then you would have to write this information in parallel. So we have a concept of partitions. Partitions allow you to generate messages in parallel, and messages are guaranteed to be strictly ordered within a partition. So, for example, you're capturing clicks from on a website from multiple users or multiple regions. You can write to different partitions in parallel, and that would allow you to capture all of the information parallelly. Now, let's take a look at how data is written and consumed. And this is similar to a pub/sub model, right? So that's what we use, very similar to certain other event brokers. And as I mentioned, we'll make a comparison to that as well. So from a producer perspective, you can publish information to our log or our topic, and all the messages are added at the end, right? So this is very, very similar to, if you're familiar with Kafka, this is very, very similar to Kafka from a conceptual perspective, right? And you can produce data to multiple partitions at the same time. And this is also very similar to existing event stream protocols within Kafka. Now, why would you want to do that? Well, that is to improve performance. That's one, and you may have multiple producers that you want to partition the data into, multiple partitions within a specific topic. That will allow you to write large volume of events into an event broker. Next, how does consumption work, right? So there is a consumer concept, and each consumer has an offset, and the offset is managed by Vast Event Broker. and it is managed in a separate metadata environment and not in a shared nothing like architecture. So we have our own metadata information and the table information that allows us to manage metadata separately from the data itself, and the consumer's offset is maintained in the metadata. That way you can parallelly, even if the consumer forgets where it last read from, the offset information can be read and you can continue to read the data. So you can have multiple consumers reading the data, and that allows you to have different consumers reading data from different offsets, and that makes it easy to consume the same data by multiple consumers. That's one advantage. The second piece is you can have consumers consuming from multiple partitions. That allows you to consume many events at the same time, improving performance and parallelism. Right. The other aspect is you can have consumer groups. So you can qualify a set of consumers as a consumer group and have that group read from multiple partitions to read large volume of events as well. Now, if you're familiar with Kafka, all of this might sound like, oh, this is just Kafka, right? And that sounds about right, because what we did is we implemented the Kafka APIs on Vast Event Broker. So you can have your existing producer consumer that is Kafka compliant and work as is on a Vast deployment. So that's the piece that is very important, because we want to make it compatible with existing widely used solutions, and that is something that is adopted across our customers, and our customers want an easy replacement for a complicated deployment, right? So that's why we started with the approach of supporting Kafka APIs and making sure the same producer and consumer code can work on Vast Event Broker as well. That doesn't mean we just took Apache Kafka and are running it in C nodes. We have actually built something from scratch and written in C++, so it's more performant than the JVM-based Apache Kafka, and just implemented the same protocols from scratch natively on Vast system. Now let's look at a bit of the history of why Kafka came into picture at all. And at a high level, there are multiple systems within enterprise, as I pointed out earlier, and many of these systems need to talk to each other, right? So it's very complicated to create different microservices or to have a set of multi-layered approach to make sure every source system is able to talk to every target system. That created the idea of a event bus kind of environment, and that's how Kafka started. And we decided to make our event broker Kafka compliant, because Kafka has been there solving this problem for a long time. Of course, at scale, there are challenges with Kafka, and that's where we want to provide really a very easy to use solution, and also a scalable solution with very little knobs to turn, which makes it easy and scalable for our customers. So we replaced all of that with a Vast Kafka compliant event broker, making sure that you can build a pub subsystem on Vast platform itself. Now, if you look at the industry, there is stream processing that is primarily being used for aggregation of events that are coming in real time. So a little bit of transformation, but mostly calculation and aggregation. From a transformation perspective, it's just that there may be too many attributes in a value, and the business doesn't need that many attributes, and you want to just drop some of them. From a calculation perspective, you just want to get aggregates within the events and things like that. And For vast event broker and other event brokers, this is true that you would want to have something that is persistent as each event is generated and can be read multiple times. So um, the other key aspect is you would want to combine both real-time data and legacy batch data that's been there for a while, right? So that enables multiple use cases, not just real-time analytics, but also machine learning training use cases and also ML inference use cases. Once a model is deployed, you can gather information from multiple events for model inference, plus monitor model drift, and automatically, if necessary, kick off ML training job based on new data that is coming in as well, right? So let's look at the traditional Kafka architecture and how we differ from it. As pointed earlier, the Kafka architecture was built on shared nothing architecture. So there is a single leader node that is responsible for multiple partitions, and there is there are partitions that are implemented, and there are copies of the data within each of these partitions. So there are at least 3 replicas. And from a read optimization perspective, there is a lot of cache management that is required, and Kafka does it well to some extent, especially at small scale. But it relies too much on hard disk and sequential reads and things like that, right? Plus, all of the other customizations in terms of rebalancing the partitions or repartitioning the data, all of that is left to a client, right, to a developer to redo it essentially. Now, if we take away all these complexities, it makes it really, really easy. The other aspect is Kafka also has a concept of transaction management to some extent, but it's not very, very efficient. So with Vast Event Broker, what we did is all of our topics slash partitions within the topics are implemented on something called Vast Database. So Vast Database is a table format, and it automatically stores data in a structured manner. Vast Database also is asset compliant, so it has its own transactions. So we don't need any additional transaction markers to manage the Kafka transactions. And you could create multiple tenants of a Kafka deployment within Vast just by enabling a separate virtual IP pool within Vast, and also creating a separate view for Kafka. A view within Vast is a data store, a isolated data store essentially. You can think of it that way. So you create a view on a bucket, and then you have a web pool attached to that, and that allows you to create multiple tenants, as many as you need, on Vast. And remember, if you need additional compute to process this data or to work through the producers and consumers, you can add additional C nodes. So it just scales linearly, not an issue. Every event broker node is mapped to a virtual IP, and that allows us to manage partition leaders ourselves without necessarily relying on third-party like Zookeeper or a RAF protocol, etc. We have our own way of reshuffling VIPs if a specific IP isn't available or a container dies. So all of that is managed automatically by the infrastructure. And it is built on traditional TCP infrastructure anyway. So that makes it really, really easy to manage within Vast platform. Now, I want to dig deeper on how topics are managed within a Vast Event Broker. Within Vast, topics are actually tables, as I mentioned before, right? So traditionally in Apache Kafka, it's all file-based, and you're essentially appending events to a file. Everything is managed internally, right? But there is no structure to it. Here with Vast, you have a specific structure of the data within tables, and all of the data that you write to Kafka can be queried through the tables, right? Now, how do vast database tables work, right? So let's take a look at some of the problems with hard disks, and then we'll dive immediately into vast database. So legacy architectures that are shared nothing when they store data, they are meant for large contiguous reads. And it's very hard for the schema to change or to update data because it's all hard disk based in many cases, right? And all of the data has to go through multiple layers for processing. That is, you have the hard disk, you have the RAM, you have CPU to get to processing, right? That's true for reads and writes. So there are multiple hops of the data. And in some cases, this makes sense from a caching perspective, but in many cases for real-time operations where you're both writing and reading, the hardware is not adequate at all, right? That's where VAST comes in because our entire platform is built on flash storage. So that allows you to directly have CPUs attached to the flash drive and be able to read the data efficiently very, very quickly. And that's both on reads and writes, right? So we manage I/O operations directly to flash without relying on traditional hard disk-based writes, hopping through multiple systems within a single node. Now, let's understand how we write data and read data to the vast database, right? So what we are trying to do is we're trying to break all traditional problems that come with rows and columns. When we write the data, we write it in a row-based format. And when we read the data, we read it in a columnar-based format. So now there may be a question in terms of, oh, how is that possible? Well, we have something called a write buffer, right? And all of the ingestion happens in row-based format to the write buffer. And all of the analytics happen to a columnar structure. And there's going to be some data in write buffer that we combine together to read to run the analytics. But that doesn't add any delay. As soon as data is written in row format, client receives an acknowledgement and the client doesn't have to worry about it. We have a background process that converts this row-based data into columnar data. Most of the data is going to be in columnar data. That allows you to run analytics at large scale. Plus, all of the real-time data that is coming in is going to be row-based, and you're able to combine both these data sets without taking any additional action. All you have to do is use the consumer protocol to access it through Kafka, or use analytical frameworks to access it from a SQL perspective. And why it matters is when all of the data is written in row formats, it is written in very high fidelity flash. So it is very reliable and is able to write large volumes of data into something called storage class memory. So this is a very efficient hardware from a storage perspective that can take as many writes as possible. And then we have a background process that launches it into a columnar structure. And this columnar structure allows our users to read data for aggregates, for column level scans, for projections essentially, and things like that, right? All of this is the technology behind our event broker. So when you write data to event broker, it's actually getting written in row format. And when you read it, we combine behind the scenes the data, both that is in row format and columnar format, right? So that way, a user doesn't have to worry about where the data is. All you care about is writing producer code and consumer code. The internal mechanisms are managed by us. And the beauty of it is you don't have to manage replicas. We system-wide, we have a process of deduplication and data reduction, which also plays into data that is written into vast database via event broker. So that allows you to create a single instance to serve all of your big data analytics and big data use cases. So at a high level, you can have a persistent layer for analytics. You can have everything for auto scaling events from an event broker perspective, and you can have traditional unstructured data also stored in our object store or NFS, right? So this platform consolidates multiple systems into one. The first is the event broker, right? So all of the real-time data gets into event broker. The second is going to be any unstructured information that you would like to store in your data lake or data lakehouse. And everything that goes into data warehouse can be part of Avast as well. So you have three different systems that can be consolidated into a one single namespace managed by Avast. And that allows you to combine these data sets for different machine learning training use cases and analytical use cases as well. This in itself has provided tremendous value to our customers, and we are seeing a lot of growth in terms of adoption of such an architecture, plus adoption of technologies like the event broker. Okay, so let's do a quick revision, essentially, in terms of what we discussed at a high level so far. And this will be a good summary section, essentially. So Vast Event Broker, real-time analytics on all events, as I mentioned earlier. It makes it really, really easy to manage because we don't have a concept of as a user or a end user having to manage anything in terms of number of replicas and whatnot, right? We have a only once approach to a great extent in terms of implementing our protocol. So you are able to also scale it just by adding multiple C nodes if there is additional performance that is required. So it makes it really, really easy to scale the event broker itself and create additional ingestion pipelines on the same platform where you can start consuming it immediately, right? So there's a lot of time that can be saved, a lot of money that can be saved because we are going to consolidate everything into a single platform to a great extent. Plus, from a storage perspective, the entire platform supports deduplication and similarity-based data reduction, which is also going to give you additional compression on the data that is coming in through Kafka. So that makes it, cost-effective, even though it's all on Flash. And from a reliability perspective, the platform itself provides a reliable mechanism, as I pointed out. Each container within a C node can have access to the entire data set. So that is also true for Kafka, as you have a couple of C nodes or containers assigned to Kafka. Even if a few of them are down, you still have access to your data, and your data is not lost because this is all on flash drives, right? So flash drives don't fail as much as hard disks. That is one. The second is we have our own erasure coding implementation that goes across the global namespace. So that allows you to efficiently store the data, plus rebuild data on any sort of failures. So from a performance perspective, with Apache Kafka, we are almost 10x faster. And with each C node, we can go up to 1 million events per second. So as you need more performance, you can add more C nodes. And this also varies with different kinds of hardware, obviously. So this is just a high-level representation in terms of what we can do. But a single C node compared to a 3-node Kafka broker is what I would say. And you can continuously increase the number of events per second on Vast C node just by adding additional C nodes to that layer, right? From a scalability perspective, you can obviously scale it in a disaggregated manner because we have the architecture that is completely decoupled. and you can add more storage or compute as necessary across the platform, and that is true for Kafka as well. The other key aspect to remember is as you write data to VAST event stream, the data into our event stream topics goes directly to VAST database tables. And that allows you to start querying that data using SQL, using Python API that we have available for the VAST database. And that instantly makes that real-time data usable. So this accelerates your time to insight, essentially, right? So what you can do with just real-time streaming and window analytics on a legacy pub/sub event broker system, you can do much more than that on VAST, where you can do that. Plus, you can combine that data with existing data in real time and make decisions as well, right? And we make it really, really easy to combine these data sets because you have federated query engines, you have APIs across VAST database that can do that. So overall, at a high level, the entire design and architecture of Kafka itself is simplified. There is no dependency on managing a separate Kafka cluster outside of your big data environment. You can consolidate those two together into a single system. And there is no dependency on third-party systems like Zookeeper, etc., as well to manage or elect leaders. Plus, you can use the same system for real-time analytics and batch analytics, and that allows you to scale things independently for both use cases. Plus, from a hardware architecture perspective, this also avoids a lot of complexity in some ETL workloads where you may previously have to take data from Kafka and then store it in a different structured table format somewhere else to run analytics instead of being able to run analytics in real time, right? So all of that is managed automatically behind the scenes by VAST as a deployment. At a high level, you have different, it's very, very easy to set it up. You just enable VAST Kafka protocol as event streams within VAST in the UI. And we also provide, multiple monitoring capabilities within our event stream functionality as well. Right. So just to sum it up, all of this is built on our DAYS architecture, and that's the key piece that enables us to consolidate different kinds of workloads, different kinds of protocols and systems on a single platform, right? So this is how we are able to run, VAST tables, S3 NFS, and the event broker in a single system, and that allows us to create this multi-tenant environment, and our customers are able to access and create an internal multiple tenant environment for different internal groups as well. That's the beauty of it. That's all I have. If there are any questions, I'm happy to answer. Okay, what flavor of SQL do you support? So today for the VAST database, we have Trino SQL, Spark SQL. So we built plugins for Trino and Spark. And we also have a table API. So we built a Python SDK to make sure that the table data can be accessed programmatically as well through Python SDK as of now. Is VAST Event Broker already available in the actual version of VAST? Yes. So starting with 5.3, VAST Event Broker is actually available in VAST, and 5.3 was released, I think, a couple of quarters ago. Okay. Are there plans and timelines to support encryption and transit encryption at rest as well as MTLS and/or Kerberos? Yes. So MTLS is going to be implemented. That is going to be part of encryption in transit. At rest already works on the VAST platform. So when you store data, you can define, encryption at rest. So that's already supported. Kerberos, I'm not sure. I think the way we look at it is we're going to work with AD and LDAP from an identity provider perspective, and go from there for user authentication. Yeah. How does performance scale with additional VAST enclosures or NVMe resources? Yeah. So from a performance perspective, I would say it scales linearly. You can continue to add as many C nodes as you need. So let's say from a just as an example, we have 1 million events per second per C node. You add another C node, you should see 2 million events per second, right? And this is just making sure everything is the same in terms of message size and whatnot, right? And you add another C node to the same event broker system, it should be 3, right? So close to that at least. Right? That's the way we look at it. At what granularity will encryption in transit be? Can some projects or paths have it? That is, I think, still being implemented. So that is a roadmap question. We can definitely get back to you on that. And right now, what we are looking at is, you would have MTLS as a mechanism to encrypt data from producers as they're writing, plus with consumers, and it would be at consumer groups plus producers that are writing to it, right? So it should be at topic level. Which existing Kafka APIs or SDKs are compatible? Can I drop in Kafka clients with minimal code changes? Yes. So the way we have built it is you can take your existing Kafka code. There is a specific version, I think it's 2.18 or something. And beyond that, you should be able to use your existing producer and consumer code as a drop-in replacement. And the only key point is going to be that you'd have to change the endpoint. So that's going to be the key. But apart from that, you wouldn't have to make a significant amount of changes when producing data and consuming data in your producers and consumers. Yeah. Any other questions? Awesome. Okay. Thank you, everyone. Thank you for your time. I appreciate all the questions. Oh, one more question. Okay. Can this be combined with vast other tools for vectorizing data for AI? So yes, but you have to understand at where this can be implemented, right? So as an example, right now we have a mechanism for S3 events. An event can be consumed by our Kafka, essentially, right? Produced to our Kafka, and then you can consume that event and launch a function to vectorize that data. And that's exactly what we do in our product called Insight Engine, right? So it is part of the workflow, but it is not something that does a lot of other things, right? So it's a event broker. It manages events. It can you can publish multiple events to it. You can consume multiple events from it, right? So that's where in the pipeline for vectorizing data it can be used, and it is kind of being used as of now. All right, sounds good. Thank you for all the questions. Thank you for making it very, very interactive. And I hope you got to learn something new from VAST. And if you have any questions, reach out to us regarding Event Broker or any other VAST technology, and we would be happy to work with you on your projects. Thank you so much. I'll stop sharing now.